Bonjour tout le monde. Hi everyone. Thank you for joining us. Merci de vous joindre à nous. Je suis Louis Baumier de l'Institut de l'énergie trottier à Polytechnique Montréal. On my name and on behalf of Natural Resources Canada, I want to welcome you to this final session of modeling project presentation, a part of the Energy Modeling Initiative. Few housekeeping rules before we start the presentations. So we have 3 presentations today. Each will be limited to 30 minutes, including the Q&A sessions. During those presentations, please keep your microphone on mute. You can post questions or comment in the chat. During the Q&A sessions, please raise your hand before asking your question. And note that this session is being recorded and the slides will be made available after this presentation, given that we have the authorization from their authors. A few words about the initiative. This initiative has been ongoing for 2 years now, a bit more than 2 years. I will invite you to visit the website mainly for those 3 links there. One that will present you the reports, the proposal that we made last year about putting in place a permanent initiative, or what we call the Energy Modeling Center. You can see all of the other projects that have been funded either last year or this year. And also for those interested in consulting or registering to our modeling inventory, you can do that on that website. So today, like I said, we have 3 projects. The first one will be by Francesco Chiari from Polytechnique Montréal. I will now give him the control of the screen. So Francesco. Yep.
Okay, can you see my screen?
Yes.
Okay. Thanks. So yeah, I'm Francesco Chiari. I'm professor at Polytechnique Montréal. I am in transportation, so that's what we are talking about today. A comprehensive method for assessing energy emission for future mobility scenarios. The whole project ended up being a bit larger than I expected. So 4 people were involved. So myself and 3 persons in my group that are here listed here, and I'll go straight away because I have the impression there are so many things, and 20 minutes or 25 or whatever, it's a bit short. So I really go straight away to the challenge. What we want to do. First, a short consideration. So transportation has been dominated by automobile, which is flexible and relatively affordable, but has huge negative externalities. And now we have novelties in the transportation system that are expected to change the status quo. On the one hand, on a technological level, we are talking especially electrification and automation. And obviously electrification is what is relevant here. And on the other hand, also we have what we call servicization, so shared mobility, mobility service, and all these kind of things. Clearly, if we want to assess seriously and fairly all this, we need to have tools that consider all this into account. And the expectation of all the situation of the possible potential future situations that we will have less energy intensive vehicles, potentially zero emission vehicles, and a reduced global fleet. What are the issues? Especially if I think from a transportation perspective, which is my perspective, well, energy and climate change impact is substantially different for different powertrains. And in terms of production and use phases. And also shared vehicles are used more intensively and need a quicker turnaround. All this means that we should, as I said, we should take this into account. But in general transportation, we completely neglect this kind of things. So we look at one scenario, we look at one day, kind of an average day, and that's it. So basically we can't take this into account. On the other hand, we have something which is probably something some of the audience is more familiar with, life cycle assessment, which is an answer to some of these questions, but a typical application in this field don't take into account the impact of changes in the transportation system and then on travel behavior. So the idea is we had is try to combine these two approaches. So on the one hand, have a model that offers realistic and self-consistent mobility scenarios. And on the other, we have life cycle assessment. So the methodology, more in detail, we have, So basically, we start from a vehicle inventory. Basically, I got this term from LCA, but basically here it means really creating a scenario. Sorry. Okay. We create a scenario with certain type of vehicles with certain characteristics, and characteristics means obviously in terms of consumption, which was interest here. Then we use a model, a transportation model, and in this case is an agent-based model, and I will explain in a second what is it, which is called MATSIM. And then we will have some results in terms of traffic flow and all these kind of things, and we'll put this into a life cycle assessment model. In the end, we will have individual impact, individual in terms of vehicles, and then we can aggregate in both over a full, an entire scenario, and also over time. And I will explain what I mean by this. All right, so here you see the main, well, the model. So it's this figure over here. It's the one that describes better how this model is functioning. So I don't think I really have the time to go into detail, but the important thing here is that we are representing travelers at individual level, that we have an iterative process within the model which allows individuals in the model, which are described through this paradigm of agent, to decide what to do. So basically they have something which is available for them, and something means different model options, and then they decide what to use according to what is good for them. And in the end, we have an equilibrium. So, and this is what creates what I was mentioning. So realistic and self-consistent scenarios in terms of transportation. And here you can see also a visualization for Montreal.
The stage is in EMS. What does it mean, the stage? Mm-hmm.
I hear some voice. I don't.
Yeah, it's been corrected. You're okay.
Okay, fine. Okay. Then this was the transportation side. Life cycle assessment, let's say priority here, it's something that is more well known, but in any case, very short.
And also the brain is.
I will remind people to please keep your microphone on mute.
Would be a good idea, yes. So LCA quantifies the environmental impacts of a product based on a cradle to grave concept. So basically all the phases of the life of this object. So I'm not going more into detail on that. So concretely, what do we do is at the step one, we have, as I was mentioning, this vehicle inventory, and we have all the relevant characteristics of the models that we use in a particular scenario. Then we have this agent-based simulation, and in the end, we have a traffic outcome, and then we can calculate how, well, the consumption in terms of energy, the use-related consumption. Then at step 3, we will add the other life cycle stages, for example, manufacturing, maintenance, energy storage, etc., which is based on EcoInvent, which is an inventory especially conceived for that. And in the last step, we can, well, add all it up, and then we can multiply according to distances in the simulation and aggregate however we want to aggregate, basically. All right. Now, the scenarios we simulated for this particular project and exercise, we had 3. So the island of Montreal, we had a baseline scenario, which is the current situation, current more or less, because the latest data we had is 2013. We'll have soon 2018. So we are basing our work on surveys, on travel surveys, and they are coming out every couple of years. So that's how it works. And then we had an EV scenario and then a shared EV scenario. And I will give a few more detail about that, those two. So in the EV scenario, basically we just checked according to a certain range, a realistic range for vehicles, how many of the trips within the island of Montreal were in this 150 kilometers threshold. And basically the large majority of them was within this threshold. So basically most of the people were assigned electric vehicles. Then we consider just one model. I mean, for simplicity, we didn't have so much time here, but we can consider many different vehicles in the same scenario if needed, wanted, if we have time. And then we added charging stations. Because obviously we are taking into account that cars are discharging and then need to be recharged. Consider also that we had a particular temperature we consider because it has a huge impact on the discharging, as you I think all know. So, but basically we can consider any particular temperature, even different temperature over the day and this kind of things. For the, well, here I call it car sharing, but never mind, is the shared electric vehicles. We assume more than double the real numbers in terms of car sharing membership for Montreal, and we adjusted accordingly the car sharing supply. We had both two-way and one-way car sharing in the simulation. And well, here you can read the different characteristics of the vehicles, and we also based on Communauto, which is the operator here, for some of the characteristics of the network. All right. So some results. I think you understand with this kind of approach, you can have a lot of different results, also simply in terms of, I mean, on the transportation side. Here, I'm really showing only what's coming out of the LCA process. So the first one, what you're seeing already, is the total energy consumption for the 3 different scenarios. And what you can see here is that the electric vehicle scenarios, as you are substituting basically almost all vehicles with electric vehicles, so the gasoline vehicles, it's the one performing better. Then you have car sharing scenario, and then obviously you have the baseline scenario. And I will give some more details on this. If you go on a single vehicle level, but over the life cycle, that's what you have. So in terms of energy, here on the left, you can see gasoline, electric vehicle, shared vehicle, and shared vehicle basically are an electric vehicle are the same vehicle, but since over the lifetime, the shared vehicle is used more, and we are considering as a, well, here, just to do this comparison, 10 years of lifetime, well, obviously shared vehicle is has a lesser impact. If I take out of the left side graph only the non-renewable part of the energy, that's what you see on the right. And here on the right is not only this, but also you have this for all the different phases of the life of the vehicle. And so one thing you can observe immediately, as we all know, is that what is used or during the use of the car, so during the travel, is the most important part for the gasoline vehicle, and is practically zero for the other vehicles, so for the electric vehicles. But you have other phases which are larger contributions, which have larger contribution for electric vehicles. All right, but up to here is just like a normal LCA, but with, again, in the back, we have nevertheless this realistic simulations we don't have necessarily normally, never mind. But an additional thing, which is very important, and that what I'm showing here is that, well, the previous graph was on the basis of these 10 years. However, shared vehicles need to be changed quicker, exactly for the reason that they're used more intensively. And this is one of the reasons why I want to do all this, right? And here we see what is the impact of this on a single vehicle level over the 10 years if we change the fleet of the share fleet every 2 years, every 2 years, every 4 years, every 5 years. And so you see, obviously, you have a much larger impact. And this is very important because, well, first because you need to do these kind of turnarounds. And this is really something that gets completely lost in the discussion usually. If you go to the scenario level, the picture is very different. So the car sharing scenarios that we were representing still are performing better than the baseline scenario, but obviously the EV scenario is much better still. And here you have both energy and also climate change. I'm not going into detail. We don't really have time for that, but that's obviously something you can do and you usually do with LCA. All right. So a short discussion. As I was saying, between the scenarios, the one with large EV fleets is the one performing better. The car sharing scenario in a way is just not extreme enough. I mean, what we are assuming is still 10%, meaning 90% of the people is still using their own cars. So if we have a higher substitution rate, it would perform better in absolute terms, definitely, and possibly even better than EV scenario. However, and that's where it comes again into play the fact that we have in the back a realistic simulation of the transportation side, it possibly limits the mobility of individuals. So it means that even if we put many cars, many more than we did available, they won't be necessarily used, or they will because they don't have alternatives, but this will be at the cost of the mobility of the people. And so, and the interesting thing here is that we are able to represent all this. So basically, we are representing all these trade-offs, and with all the information necessary in the end to decide how to deal with them. And so the results are a demonstration that this combined framework offers a fair and comprehensive assessment of future transportation scenarios. And I explain this fair because it takes into account the implication of a possible larger diffusion of shared vehicles. That's what I was saying, the intensity of use, because otherwise it's completely unfair in a way. The kind of comparison that we are routinely doing in transportation when we talk about electric vehicles. It is comprehensive because we account, well, this is what LCA does generally. We account all the phases of the life cycle. And is based, as I've said already a couple of times, on realistic, behaviorally sound transportation scenarios. So we explicitly represent individual constraints and preferences, and we also represent, and another important point that you will not see in all transportation models, all transportation modes and how individual can trade off among them. So that's another very important point I'd like to stress. So we would say that the tool should be an important tool designing and evaluating transportation pathways in the transportation sector. So energy was the point here, clearly, but specifically for the transportation sector now. And we mentioned, we show here all the impacts of different systems, and basically in the end it helps defining what is the most desirable future. And as we have seen, it might not be as obvious as it is, well, not exactly as we would expect. So I go back, a short summary, I go back to the motivations in a way. So we need an holistic approach to assess emissions and externalities in general, so energy consumption and many other, in an ever-transforming transportation sector, and especially that several parts of the system might change. So we can't really evaluate the transportation system, which is a complex one, which has many different parts, and many of them are changing or about to change, or that's what we expect anyway. And we cannot just take in isolation one of these aspects, but we have to take all of this because they also have several interplays, so we can't just do that. And obviously we won't find a single model that will capture all. And our idea, I think, is, as we showed here, is that this integration or combination, if you prefer, of LCA and MATSIM, so this agent-based simulation, is an important step in this direction, in our opinion. Okay, I think I went through this already, basically. So what agent-based model does and what doesn't, and LCA. So I just have the last slide here. So to conclude, what we can already do is to use MATSIM, so this agent-based simulation output, with travel details of the whole vehicle's fleet for an average day, and feed an LCA calculation tool, and show and do the kind of assessment that we just showed. What we are trying to do in the future, well, on the, I would say, the more simple side is create several MATSIM scenarios for different situations, because again, here it's just an average day, but obviously over 10 years, you don't just have an average day, and also the definition of average, I mean, we could talk hours about that. So go in more detail on that, days of the week, seasons, transformation path of the path of the transportation system. So also over time, how it changes, etc. And modify the tool in order to have a more accurate LCA. So one that takes into account all this difference over this span of 10 years. And then the next thing, which is much more ambitious, is trying to extend the model to energy energy consumption related of other human activities. Since MATSIM basically, so this simulation provides daily plans for each individual. What does it mean? So we simulate transportation based on the assumption, well, basically it's not the assumption, it's the reality that people move around mainly in order to perform activities at different places. Now, these activities obviously are also what create energy consumption. So if I'm in a particular building and many people are, we have a certain consumption, and if it's completely empty, we have a different consumption, etc., etc. And it also depends on the kind of activities and all these things. And we do have a very simple, but we do have a modelization of all this. So the idea would be to go down this path and try to add other human activities and try to capture more and more energy consumption in general, and not only the one related to transportation. So that's what I want to tell you today. Thank you for your attention, and I'm happy to take questions if you have some.
Well, thank you, Francisco. That was a very interesting presentation with, I would say, counterintuitive conclusion, at least to me.
Yeah, I guess that's the point a bit.
Yeah, that's exactly why we need to do modeling, right? So,
Yeah.
So I guess the next question would be, if you integrate other individual activities, will it be, am I better to use a carpool or a car sharing to go eat a salad, or keep my individual small car to go eat a steak, right? Which one would be?
Well, perhaps it's a kind of going a bit too far in terms of level of detail, but I mean, yes, the idea, I mean, you know, it's really saying, okay, in the end, all energy consumption relates to some human activity.
Yeah.
What we do here, it's obviously because we want to simulate transportation, but we have a very simple, but still a complete representation of human activities over a day. So, I mean, obviously we have to, you know, to connect many dots here. We need to add many sub-models, but yes, I mean, that direction. There is a question in the chat, I think.
I'm trying to find it.
Yeah, okay. Did your simulation model, so the first is Claire Isabel. Did your simulation model determine what will be the ideal percentage of shared vehicles that will make the SU scenario more energy? That's the, you know, that's the jackpot. Yes, that's a very relevant question. That's for now, no, we are not. We are, you know, it was kind of a tentative for the moment. So also because you have to consider that this kind of simulation is computationally very costly. So it's difficult to really optimize in terms of scenarios. You get an idea, you get which direction you should go, but really optimize, strictly speaking, it's difficult. But obviously, yes, it's a very relevant question. I go to another one, Eloise.
Yeah, what's the difference in lifespan between car shared and individual owned?
So on the basis I showed at the beginning, it's the same. So it's 10 years. Or the question is in reality. In reality, is like a bit more than double the life of a private vehicle. So that's more or less the data I have. In reality, I mean, it's not something that you kind of find, but talking to operators, more or less, they have 3 to 4 years turnaround. So
one more question: any plans to do a study with hybrid vehicles since they will not require a charging station?
They weren't here. They weren't considered here. There is a contribution. Well, contribution is a jargon word, but within the MatSim simulation, we can simulate also hybrid vehicles. And I have a separate project with Hydro-Quebec, where we are looking at also at electrification from a different perspective, especially in terms of impact on the power grid. And we'll look at this kind of things too.
Mm-hmm.
Okay, I don't know if there is time for any other questions.
Yes, we still have 2 minutes. So did you take into consideration, in addition to charging station, do you take into account like parking spaces or installation outside power plants?
Okay, well, here I have more or less the same answer in the sense it exists in the simulation. We didn't here because it costs even much more if you add this. But it's not even that in this case, is that I don't have yet this, the information. I know where to find it from Montreal, but I don't have it coded in the model yet.
Okay, thanks. And one final question, would you consider electric rail in future modeling? I mean, like catenaries or something like that?
Yes, I mean, this is kind of the easiest part. I mean, in a way, I mean, in the sense that, you know, you have the trains in the simulation, not here now, but you have in general. Yes, you can do that. I mean, here obviously it's not really relevant, but in other, I mean, the simulation is applied to many cities around the world. You have all modes basically, so including, yeah, local, but even long distance trains. So you have everything basically.
Good. Well, we have a few seconds for one more question. If anyone wants to ask a last one.
I don't have the time to read it, so I guess you.
Well, if there's no more question, I will thank you, Francisco. Thank you very much.
Thank you.
And it will now be time for our second presentation, this time from the University of Victoria.
Sorry, bye.
Bye-bye. So our second presentation will be by Cameron Wade from the University of Victoria, sorry. And we'll talk about the similarly costly but techno-economically diverse decarbonization pathways. So Cameron, yes, you are there. Okay.
All right. Thank you. And thanks, Francesco, for the great presentation. I'm just going to take a second and pull up the presentation here. Are you able to see?
Yes.
A PDF? Perfect. Okay, so thanks everybody for tuning in. My name's Cameron Wade. I'm a PhD candidate at the University of Victoria, working with doctors Peter Wild and Andrew Rowe. And we work out of the Institute for Integrated Energy Systems there. And so today I'll be talking about an ongoing project that's really about exploring the near optimal solution space of power or energy system optimization models. And briefly, I'm going to give a little bit of introduction and context to electricity system or energy system planning problems and some of the problems that they currently face. And then we'll talk about a methodology called modeling to generate alternatives that can kind of systematically look at near optimal solutions. And that's really the heart of what we'll be talking about today. And then we'll talk about the model. And so there's kind of two separate pieces to that. There's talking about the modeling to generate alternatives model or methodology, which is kind of separate in and of itself. And then we'll also introduce an energy systems model of Western Canada that essentially serves as the case study or the application of the modeling to generate alternatives approach. And then we'll spend some time kind of going over the results of that and really trying to not analyze the results so much as an energy systems model results, but what modeling to generate alternatives can bring to bear on this type of analysis. And we'll wrap up with some concluding remarks. So perfect. I'm starting with energy transitions are difficult, right? If we're going to be compliant with net zero ambitions or the ambitions set out in the Paris Agreement, there's going to be a complete and total overhaul to our energy system.
Excuse me, Cameron. I think
yeah.
we don't see the right screen. We see just a single graph right now.
Interesting. I'm going to have to stop sharing and reshare. Oh, here we go. Sorry, it's interesting. It doesn't do screens. It does. Okay, sorry about that, everybody. This is all you missed. Not a whole lot. So this is the page we were on. Apologies. Right. So this transition is going to be difficult. There's likely going to be an entire kind of energy system overhaul required. And a lot of that is likely going to take place in the electricity sector as more and more end uses are electrified. And what we do know about the electricity sector is that, you know, it's full of capital intensive and long-lived assets. Yeah. And so, you know, these first 2 points together, when taken together, kind of imply that today there's going to be lots of large, sizable investments that are going to have to be made under deep uncertainty. And so that's a problem facing, that's the problem facing us. And so what do we do? Well, we use energy system planning models as decision support tools. And so, you know, there's tons of different types of models, each with their different kind of features and drawbacks. But what we're talking about, at least in this context, is the planning model. So on the right-hand side, we see a figure that kind of, let's say, compartmentalizes different types of power system models anyways. In the axes, we have time frame on the y-axis, going from kind of milliseconds up to years. And on the x-axis, we have the level of detail, whether it's kind of system level detail on the left or component level detail on the right. And so these are some popular models that I'm sure some of you are familiar with. But what we're kind of talking about in this context would be the top left of capacity planning models. So, you know, what are the optimal set of investment decisions in kind of a coarse representation of the operational decisions, you know, to get us to where we need to be by 2050, for instance. And then on the left, this is kind of trying to extrapolate that to an energy systems format. So thinking more broadly than just the electricity system, thinking about some of these hard to decarbonize sectors. But in this, there's kind of the elephant in the room, right? We don't see on these past two diagrams anything about uncertainty, but we do know, you know, if we're going to kind of look 30 years into the future, there's tons of uncertainty that we're facing, and that we're going to have to somehow, you know, either ignore or choose how we incorporate that into our models and our decision-making processes. And so when it comes to addressing uncertainty in energy system planning models anyways, it's nice to kind of partition uncertainty or separate it into two forms. And so on the one hand, you have parametric uncertainty. So this is just uncertainty in things that we just simply cannot know. So, you know, the future costs of natural gas or other commodities or investment costs required for, you know, wind, solar, whatever it is, or what the future weather climate is, or, you know, geopolitical relationships, anything like this, right? That's all considered parametric uncertainty. And there's lots of great methodologies to deal with that, whether that's stochastic optimization, if we're able to at least, you know, determine what the distributions of these uncertainty or sources of uncertainties are. You know, things like Monte Carlo simulations, sensitivity analyses, method of Morris, stuff like this. Separate from parametric uncertainty, though, we have structural uncertainty, which is kind of the manifestations of mathematical abstractions. So we know in many of these planning models, they're formulated as linear programs. And I studied math, and one of my favorite quotes is, we spend so much time studying linear phenomena, but, you know, I think the quote goes, you know, separating things into linear and nonlinear phenomena is like separating the world into bananas and non-bananas, right? So we're constantly making assumptions in trying to linearize things in this case, right? And so we're losing some reality when we're doing that. And so that's what structural or uncertainty is in this context, is the uncertainty that's kind of left in the models by us doing our mathematical abstractions. And we see that in these types of models by kind of knife edge solutions or penny switching and things like this. And so one method to deal with that is modeling to generate alternatives, which is what we'll be talking about today. And so what it is, it's essentially a systematic methodology to navigate the near optimal solution space. And so what it does is it first defines the near optimal solution space by solving kind of the optimization problem. So in this case, say an energy or capacity expansion problem. And then from that, it defines a near optimal solution space. And then it kind of explores that space for different solutions that are not necessarily optimal, but it's close to optimal, but they could be really distinctive by some metric. And so the intention then is not to get an optimal, a singular optimal answer per scenario. It's instead to kind of extract a portfolio of alternative solutions that exhibit the degree of flexibility in the model solution. And so an application is to elucidate to energy system planning stakeholders the breadth of possible futures that exist within the, let's say, negligible cost differences for a given scenario. And so in the abstract, it applies to all optimization problems. I'll get to that in a minute. It was introduced, the method anyways was introduced 40 years ago and has recently been starting to be applied to energy systems or power systems planning problems. But as far as I'm concerned or aware anyways, that there's been no application in a Canadian context as of yet. So let's talk about the model. Simply put, this will be pretty high level. It's energy systems planning models tend to be optimization models, and in the most general sense, this is the kind of the canonical form for a convex optimization problem. You're minimizing some function f, which is assumed to be convex or linear, subject to some family of inequality or equality constraints. So what MGA does, or method to modeling to generate alternatives does, is it's a three-step process where the first is solving this original optimization problem. The second step is defining a near optimal solution space by using the optimal solution of the original problem as an anchor point. And then the third step is to define a new objective function or a search direction to select a new near optimal solutions in that near optimal space. And then you can iterate a number of times to select different interesting solutions. And so graphically, this is kind of what it looks like. So you can imagine here's an optimization problem. You're trying to minimize the value of f of x, say, and it spits out the problem or the optimal solution of x star with f of x star as the minimal, say, cost in this case. So what we do, the second step, if you remember, is encoding a new constraint on the MGA problem by essentially taking the previous solution and encoding that as a constraint. So what we see here, a little bit mathy, but I'm not sure if you can see my mouse or not, but in this constraint in the boxed problem, the f of x minus 1 plus epsilon fx star less than or equal to 0, that corresponds to this dashed kind of bronze bar in the problem. And so that essentially imposes two new constraints, these bronze vertical bars that kind of limits the solution space of this updated problem. So now what this updated problem is saying, okay, let's minimize some totally separate function, m of x, subject to this new updated set of constraints, all the same old constraints, but with a couple new constraints that essentially anchors this or defines this near optimal solution space. And then once you have that defined, you can define, m of x, your new search direction. So in this case, you can imagine, say, okay, let's minimize x in this near optimal solution space, and then your new optimal solution would be x epsilon minus. A little bit abstract, but I think it might be instructive to kind of understand the theory of what's going on. So we applied it to an energy systems planning model that I won't really get into detail. It was based off these two studies that I provided on the right. Essentially what it is it's an energy system, or more or less a power system model of Alberta and British Columbia. Their current systems were going out to 2050, and a really kind of loose policy scenario, just the current federal carbon tax and a mandate to electrify the entire road transportation fleet of British Columbia by 2050. And so, there's lots of information about that model, but that's not really kind of what this MGA presentation is about. So interested readers can, read the report or look at these 2 studies for even more detail of how those studies were set up. But briefly, to give you guys an idea, here's kind of a template or a schematic of the energy system we're talking about. So this is the combined BC-Alberta system. So essentially, there's an array of energy sources that get fed into or consumed by transformer technologies, in this case, mostly power generation, hydro, biomass, a bunch of thermal generators, and so on and so forth. What I will say is that each province is represented by 1 node, but there's 7 wind resources available in each, and I think 4 solar PV resource sites in each to get a little bit of spatial variation there. And so, that produces electricity, which can meet, let's say, conventional electricity demand, or electrified, the electricity demand coming from the electrification of the transportation sector. And really quickly, how the electrification of the transportation sector worked is that essentially it was an exogenously defined conversion from the current status to 100% electrification of medium, light, heavy, and passenger vehicles. With I won't get into too much detail there, but I guess what's important is that for the medium and heavy duty transportation, it's assumed to have a flat load or a static load, so its charging profile is flat throughout the day, whereas passenger vehicles and light vehicles follow a typical daily charging profile, just taken from literature. Okay, and so how are we applying MGA or modeling to generate alternatives to this application? What we want to do is find solutions to this energy system optimization problem that are similar in cost to the optimal solution, but really differ in system composition and operation. And so what we're going to do, maybe starting on the right-hand side here, is we first determine a search direction for this MGA method. So that was the M of X in the little MGA schematic. And we decided to minimize or maximize the total activity of the following groups of technologies. So that's wind, solar PV, battery, gas turbines with or without CCS, and transmission. And so those are all done separately. So one MGA scenario, for instance, says, okay, let's maximize in the near optimal solution space, let's search in the direction that maximizes total wind generation over the 30 years in question. And that's done for a number of these, what we call slack variables. So essentially the slack variable essentially just translates into what percentage premium are we willing to increase the total system cost. So we do that for, say, 1%, 2%, 3, 4, 5, 7.5, and in a 10% premium. So we can look at some results, and maybe that will make kind of the process a little bit more clear. And we can just start by looking at the results for the base case. And so this is just for the normal case that, okay, yeah, we've got our situation that we talked about. We're electrifying the road transportation fleet by 2050. We're going to optimize, and this is the optimal solution. And so you see a few things essentially. On the left is the energy plot, and on the right is the capacity plot. And so we see coal phase out in the energy and capacity plots by 2035. And we see initially anyways, some combined cycle with CCS being built, which is interesting. That didn't used to come up in the model, but now with the updated carbon tax up to $170, that seems to be the most economical immediate addition, which is interesting. But past that, we see essentially a large increase in wind build out to meet the increase in electrification, followed by a substantial build out of solar and batteries in tandem. The batteries are represented by these kind of light pink colors on the top. Again, we're not really here to analyze the base case, but this just gives you an idea of the system composition under, at least costs. The model also, we use representative days. So this model uses 10 representative days and models every 5th year. And so that also gives us the ability to kind of get in here at hourly resolution and look at what types of electricity system dispatches is occurring. And so again, we won't spend too much time in here, but what we do see is that this is for 2045. And what we do see is that curtailment is a system feature by 2045 with all of these renewables on the grid. So I guess it's good to know that the black line is the conventional electricity demand. The kind of thick hashed line is the medium duty and heavy duty freight electrified transport demand. And the thin dashed line is the electric transportation demand for light duty and passenger vehicles. And so a couple things we see anyways is that, yeah, curtailment is a feature of the system. And you're probably asking, why is there curtailment if there's dispatchable hydro there? That's because there's certain rules for the hydro. There's some must run, there's run of river, and there's kind of a total energy budget that has to be obeyed over the year. So that's why hydro isn't as flexible as you might think it would be. What else do we see? We see that there's also, we can kind of capture the use of peaking resources by using this representative day format. So if we look at the top left, so this would be February 11th, we see that there's really a terrible wind and solar resource, at least in the evening. And so that's when we see the battery being dispatched to meet the evening peak, and the open cycle gas turbine to meet that evening peak as well. And that's actually the only time of the year that that's dispatched. So that's kind of consistent with intuition anyways. Okay, so now if we want to think about some alternatives, we'll just start with an illustrative case of imagining, well, what happens when we maximize total solar PV activity at a 2% cost premium? So this is the MGA case where we say, okay, we've used the optimal solution that we just spoke about. Let's allow a 2% cost premium that defines this near optimal solution space. And the direction we're going to look in for a new solution is by maximizing the total solar PV generation over the 30 years. And then this would be your new solution or an updated solution. So really similar in cost, but different in composition. We see there's a lot more solar, and we actually see there's a lot more battery on the system as well. What else do we see? Right, and we also see it. There's an increase in total capacity on the system as well. So if we look at the right-hand plot, by 2050, there's almost 100 gigawatts of capacity on the system. But that's really because of a few reasons. First is that solar PV is substituting other technologies that have much higher capacity factors. There's an increase in system losses because there's lots more electricity running through batteries, which have an 85% round trip efficiency and transmission. There's increased levels of curtailment in this type of system, and solar PV provides nothing to the reserve margin. So the system still needs to build other technologies to meet the reserve margin constraint. So this just gives you a flavor of what MGA can do. Based off the optimal solution, what are other kind of near optimal solutions in terms of total system cost that look different in system composition? Similarly, we can look at kind of envelopes of the future system. So I'll be brief here, but if we focus on the wind plot, what we're doing here is we're looking at the total activity of wind for different slack values or for different cost premiums for both maximizing, so that's when it goes up, or minimizing when it goes down, the objective function. So what we see is that in the optimal solution, wind provides about 1 petawatt hours of energy over the 30 years. Now by maximizing wind at a 1% cost premium, that gets bumped up about, what's that, nearly 80%. Other features you can see here essentially is the marginal decline of, or the decline in marginal value of wind as it's increased on the system, and that even at a 10% cost premium, you still can't force wind out of the system. So wind is essential. Similarly, we see that it's actually quite cheap to force solar and battery out of the system. These are not essential requirements of the system. Likewise, CCGT has gas turbines have a very kind of niche role to play. They're going to exist in the system. There's not going to be much of it, but they're more or less required. In the interest of time, I think I might skip this plot, but this plot, if you'd like to look afterwards, essentially just gives you a whole bunch of different possible futures of the energy system composition at different kind of cost premiums and search directions. But this will give you a flavor of what's possible. But I'm skipping that just to get to this figure, because from this type of analysis, we can also get to some system level insights. And so what this plots the correlation between different types of technologies when you consider the results of all of the different kind of scenarios that we ran, or all the different essentially combinations of minimize, maximize, different slack values in different groups of technologies. So there's actually 70 alternatives that we ran. And so when you look and when you plot the correlation between technologies, you can kind of get some system level insights. And so generally speaking, what we mean here is if a pair of technologies have a negative correlation, that kind of indicates that they're substitutes. So in this case, we see that combined cycle gas turbines and open cycle gas turbines have a very negative correlation, meaning that in any situation when CCGTs get increased, that's to the detriment of OCGTs, and that's consistent with intuition. What else do we see? Well, we see wind and solar are actually fairly negatively correlated as well, which kind of gives us the insight that at least in this system, they're kind of competing technologies. When wind is increasing, it's to the decrease or to the detriment of solar. On the other hand, we can kind of see complementary sets of technologies by looking for positive correlations. So we see that solar and batteries are fairly highly correlated, meaning that in the situations when solar, when there's an increase in solar activity, there's a large increase in battery activity and vice versa. Lastly, we see a couple more interesting bits where there's a slight negative correlation with wind and battery. And that kind of indicates that wind probably needs longer duration energy storage to balance its intermittency. And so there's not really a strong correlation between storage in this case and wind. But what we do see is a slight positive correlation with wind and transmission, which indicates that transmission can actually come in and balance some of wind's intermittency. So briefly wrapping up, where are we? Well, it's currently under development. I was hoping to pull up a web browser. So this is just a screenshot from kind of an interactive web browser where you can kind of go through all the plots and get different information and zoom in and zoom out and whatnot. And so that's currently under development. And insofar as concluding thoughts, well, I guess I got to be quick here. Essentially, what policy gaps does this fill in the usability for policy design? Well, we really hope that this type of analysis can illustrate to kind of energy system planning stakeholders the portfolio of opportunities that exist. So you give one single scenario or set of input assumptions, and we can look at this broad portfolio of system compositions that are really, really similar in costs. And taking into account the parametric uncertainty, they're essentially all the same cost, right? And so this is good because it kind of gives an indication that for the set of assumptions, we're not destined to this one particular path. There's actually kind of quite a bit of variation on the path we can take. And quickly, the benefits from being integrated into a national modeling platform. Well, one benefit is that the modeling to generate alternatives methodology is not tied to a particular model. So I used it on a model called TOMOA, which is similar to like TIMES or Markle or Osmosis or something. But it can be seen as kind of a separate model that can be plugged on to different types of models, be they capacity expansion or transportation or land use planning or what have you. It's just a way to kind of explore that near optimal solution space and give people an indication of kind of what's a possible future, or what's the set of possible futures for this input scenario. So I think that puts me at around 25 minutes. So I'll stop there, but I'm happy to go back and answer any questions.
Well, thank you, Cameron. That was a very interesting presentation. Yeah, you're exactly right. We still have 5 minutes for questions or comments. So the floor is open.
Oh, I see there's some stuff in the chat.
We just posted the link for, there was a question about will the presentation, the slides made available, they will be posted online. And there's the URL that is in the chat. So Norma, you have a question?
So you showed results for Alberta and British Columbia.
Mm-hmm.
Is there for other provinces, or because it wasn't clear from your last slide, so that's why I'm asking.
Sorry, yeah. No, so we applied it to an energy system or power system planning model of just Alberta and British Columbia. Okay. Yeah. But kind of what I referred to at the end is that this was just kind of a simple case study to show what type of tool it is, but it can kind of pretty easily be, you know, tacked on to other people's models if it's a pan-Canadian model or what have you.
Okay. I think it's very interesting, this approach of
Yeah, there
which
is
is more than simply sensitivity study. Yeah.
Mhm.
One question from the chat: did you consider CCS technology for example, attached to natural gas generation?
Yeah. So, are you still able to see my slides right now?
I stopped the screen sharing, but you can.
Okay. No worries. No worries.
You can restart it.
Okay. It might be a little bit helpful to. You know what? I'm so bad with Zoom. I won't bother. It won't be that helpful. But to answer your question, yeah, we modeled combined cycle gas turbines with the CCS technology, and what we actually saw is that there's essentially kind of a capacity and energy deficit around 2030 because coal, since the Alberta system is being modeled, coal is quickly getting out of the system. And there's an increase in electricity demand from electric vehicles coming online. And so what we see is initially that's actually met with natural gas, with CCS. And what's super interesting is that I just reran all of this stuff in the past month or two with the new federal carbon tax going all the way up to 170. And prior to that, it was actually, we didn't see hardly any CCS in the system. So now with the updated carbon tax, we actually did see some natural gas with CCS coming into the system at 2030 to kind of meet that increase in demand.
And interesting, that's interesting. So some more questions? Yeah, I would like to go again. If there is no question, I would go well, that may be for an offline question, but how difficult would it be to combine that with or couple that with let's say a time Markle model, for example? But I guess we can address that offline if it's too long of an answer.
Yeah, it's a good question. I mean, so there are the reason I went with Tamoa for this model is because it does have MGA kind of in its ecosystem. Now I had to do some, go into the guts and change it around for which search directions to go into. But generally speaking, it wouldn't be a huge project. It would probably be on the matter of like a month or something. All you'd have to do is essentially go and change the syntax for their optimization model. But it's nice because it's its own independent thing, and then just interfacing it to different energy systems models requires minimal effort.
Okay, thanks.
Yeah.
Okay, we have 2 more minutes for questions.
There are questions in the chat box, but you can just open your microphone and ask the question. It's easier.
Yes, Claire Isabelle, you have a question if you want to open your mic. And after that, Stephen.
Yeah, sure. So my question was, I thought it was a very interesting presentation, by the way. I was just curious to know whether you had anticipated maybe using this type of model for helping independent energy producers, especially in the field of renewable energy, to sort of anticipate their curtailment requirements?
That's an interesting question. I've never really thought about it. Yeah, I'll think about it and maybe get back to you if I
no worries.
But yeah, no, because usually the way that I'm thinking about it anyways is more kind of capacity building and because what's nice about this is that, for say in this case we're trying to do some planning for Alberta and BC, and these are 2 places with totally different resources and people, and so what often happens is if you give kind of one scenario, it spits out one pathway and someone's not going to like it, and that's not very constructive. So what this can do is you give it one scenario, it can spit out a bunch of different pathways that are essentially equally costly, and then you can kind of then people can kind of bring their values and things to bear on it, and kind of see what they want to see from it. That's all kind of being generated from the same set of assumptions. So I kind of think about this as at a more kind of higher level, but I'm sure that it could be applied in kind of independent power producers and kind of merchant generators and things as well. I just haven't thought about it like that.
Thank you. If you can answer by yes or no, because we have like 30 seconds. Did you find any correlations and inverse relationship at different cost premium?
I didn't look into that, but that's a great idea.
All right. Well, that's all the time we have. Thank you very much.
Yeah, thank you.
And again, the slides will be made available later, either today or tomorrow. Thank you. Okay, now our final presentation of the day and of the year, I should say, will be by Clara Kaiser-Brill, Ramata Ba, and Joanne Whitmore. So I don't know who's going to be sharing the screen, but it is available for you.
Ça va être Clara to share the screen.
Yeah, I'm sharing my screen now. Can everyone see it?
Yes, it's getting up. Yes, we see it.
Perfect.
Donc,
so it will actually be the three of us speaking, Joanne starting and then Ramata and me.
Excellent.
Thanks. I'm not putting on my camera because I have to speak really close to my screen in order for you guys to hear me properly. So first of all, well, thank you for everyone to be here. We're going to be presenting results of a first ever simulation of the eHighway technology to help decarbonize heavy freight transportation in Eastern Canada, specifically on the highway corridor between Quebec City and Toronto. So Clara, if you can go to the next slide, please. So this is basically the structure of our presentation. Just give a brief overview of the context, why we decided to look into this, as well with the objective of the study. And then we'll present the technology because it's not something that's been very well looked at in the Canadian context, or North American for that matter. Then we'll present the model, methodology, assumptions, some of the key results and conclusion. And maybe as a first caveat, maybe to mention, is that the report has been published on the EMI site as well as the Chair in Energy Sector of HEC site, but we had someone who read it who found some mistake, and fortunately we were able to review some of the simulations. So it's changed some of the results, and so we're going to update the report and put it back up. So if you have printed it out or shared it or whatever, just grab that first version, and we'll have the newer version that will be coming out soon. So perhaps just before I start on the introduction and the context, this was a good collaborative work between so the Chair of Energy Sector Management, myself, who is a senior researcher at the chair at HEC, and a team of experts at CPCS, which is a consulting group focused on transportation, logistics, and planning. We also had the support of Normand Mousseau, who is a professor of physics at the University of Montreal, but also the academic director of l'Institut Énergie de Trottier. But for the simulation, the team was really Clara Kaiser-Brill, who is the global director of CPCS Power Units, and she's the one who led the simulation. She's an electrical engineer by training, and she's also had the chance to work on some power supply projects for railways and infrastructure through catenary system in the past. There's Ramata Ba, who is also a consultant at CPCS, but she focuses on applied financial economics. And then there was Ashok Kinjar-Rapu, who is was working on the simulation on the GIS, sorry, work of this study. So for the context, basically, before we dive in the technical part, which is going to be presented by Clara and Ramata, as you know, freight transportation is probably the most challenging sector to decarbonize. Heavy truck represents 8% of national emissions in Canada, and since 1990, it's tripled. It's difficult mainly compared to personal transportation because it's highly complex when you consider logistic chains, regulation, cross-border traffics, and just how technologies have to be interoperational between different jurisdictions. it's also extremely disruptive when we have to start transitioning to decarbonized systems, because it's so important for supporting our daily economic activities. So, you know, the need to change is important, but it could have a big impact also on economic activities. But on the other hand, achieving Canada's net zero emission goals by 2050 will absolutely require decisive action in this sector, both technologically, but also logistically. Otherwise, it's just, we won't be able to do it. So, as some of you know, the current initiatives are pretty much insufficient to place Canada on a clear path towards zero emission in road freights. The biggest sort of approaches that have been used by the government has been, for now, to rely on the carbon tax, which of course is a very important initiative, which is going to be ramping up to $170 by 2030. We have also improving standards of heavy trucks that are in place, but it's often difficult because we have to follow the US, given that our market is pretty small compared to them. There's subsidies for alternative trucks technologies also that the federal government has put for, mostly for natural gas, but unfortunately it only reduces at best emissions by 17%. And also hydrogen, which has also quite a lot of challenges. And then the other initiative is the clean fuel standards for regulating minimum levels of biofuels. But even the government only foresees to have 13% reduction below 2016 levels in carbon intensity in liquid fuels by 2030. So all these are super important, but they're not enough. So the limits to the approach has led many either decision makers or university researchers to look at other options, and that has been the eHighways. The eHighway is the overhead catenary system that directly powers heavy truck engines that are equipped with pantograph on dedicated corridor highways. So this has been very much looked at in Europe, or at least more so, but it has not so much in Canada. So the objective of our study was to simulate the potential of this eHighway technology for, like I said, the stretch of what's called l'autoroute 20, which is mainly what connects Montreal to Quebec, and then the Highway 401, which brings us from Montreal to Toronto and the US border. So it's a stretch of about 1,300 kilometers. And to do that, the simulation was based on a GIS analysis of current flows of heavy vehicles according to the present road capacity on that stretch of highway. The study considers hybrid diesel catenary electric trucks because one of the sort of interests, which we'll describe later, is that the truck is not just purely, it's not just purely electric, it can also be, of course, running on a different system once it gets off the main catenary highway. So it can be diesel, or it can be eventually battery, or it can use other biofuels, things like that. And so in this case, we considered just the hybrid with diesel on Class 8 trucks and above. And this is a project that is actually a first step in a proposal which is much broader, that was developed by HEC and CPCS in collaboration with government, the Quebec government mainly, and university and private partners to compare the cost and potential of different decarbonizing technologies, which we hope can include eHighways along with others. So on that, I will pass it to Clara.
Ramasa, actually, who will explain what is this technology.
Yeah, thank you, Clara. So in terms of the eHighway concept and how it works, it consists of using catenary technology to kind of build an electrified highway. And catenary technology is something that has been used for years now in transportation, namely in light and heavy rail, as well as trolleys. And in Canada, it has been used in urban public transportation as well. So it's something that is known and already mastered. The novelty is really its application to road transportation. So it consists of using overhead wires to supply electricity to vehicles through a pantograph that is installed on the roofs of the vehicles. And outside of electrified roads, these vehicles will use a secondary source of energy that can be either diesel or electric with, for example, a long-range battery. And that's what's really interesting, is the flexibility that the concept offers, in the sense that outside of electrified roads, vehicles or trucks that will be using the technology can still function and circulate. And at the same time, having the electrified highway doesn't prevent regular trucks or regular vehicle to travel on these roads as well. And then if we move on maybe to the relevance of the concept on the next slide, please, Cara. So there's different characteristics that make the highway concept relevant in Canada, but really what it comes down to is, one, that we have a linear transportation network and relatively few key corridors to focus on, and two, the fact that we have access to clean and affordable electricity in comparison to other countries. And in that sense, that technology, again, the CAN technology in itself is not new, but its application to road transportation is the novelty here. And if we go to the next slide, you can see on the map, there has been, Claire, can you just go to the next slide here? Thank you.
Sorry, there's a delay.
Yeah, okay, thank you. Yeah, so as I was saying, there has been a few pilot projects happening around the world testing the highway concept. And mainly they have been engineered by Siemens, who's really at the forefront and kind of the pioneer in this industry and the application of the technology. So Germany is at the forefront, and they have 3 ongoing pilots. And they also have set a target to reach 4,000 kilometers of overhead catenaries by 2030. You also have Sweden that is following suit. They already have an ongoing pilot project and a set target of 2,000 kilometers of electrified roads by 2030 as well. You have a few other countries such as France, the UK and Italy, who are looking more into the concept, and it's definitely something that we expect to see more and more of in upcoming years. So I'll let Clara explain kind of our approach and how we have configured the simulation.
Thank you, Amata. So going through our approach to the simulation. So the objective here was really to focus on one corridor and see what happens if we apply the technology on that corridor. So we took this corridor that goes from the US border and up north. After even Quebec City, we really looked at the corridor in its entire extent. And we used real truck flow data extracted from public database from the Ministries of Transportation in Quebec and Ontario. One first challenge that we had is that we want to focus on heavy trucks, class 8 off, but this information is not really available from existing data, so we had to use approximations to arrive at the numbers that are here. Also from more than 1,000 down to a bit more than 1,000. That's the number of trucks per day. And using this GIS-based information on the traffic between the main cities on this corridor, we then run a relatively simple simulation to compare the costs and benefits of eHighway. So the model we use is an model. The techno-economic eHighway, a scenario for deployment and adoption industry, and as an output, we get the costs, both in terms of investment and operations and maintenance, including the cost of electricity. And on the benefit side, we get important savings on fuel, as well as to which a value can then be attributed. So the economic pyramid we've used for the eHighway as it's centuries old technology, but its application to highways is relatively new. So we have turned to view of the literature to give information on the technology and its key parameters. In terms of electricity consumption on the eHighway, we found numbers ranging from 1.2 to 1.9 kilowatt hour per kilometer, and we selected a median assumption, 1.5, considering that the highway, the corridor that we're looking at, does not present any specific challenge. So we think this median number is a good approximation. The infrastructure cost is really a complex question. In the literature, we found costs ranging from 2.4 million of Canadian dollars to 4.8. The difficulty here is that there are different ways of configuring eHighway that will correspond to different truck flows, different functionalities as well. So like, for instance, the highest number here corresponds to an infrastructure that can accommodate extremely heavy truck flows, much heavier than what we have here. So it would be too much for Canada. On the other hand, many cost information that we have comes from Europe, and we know that infrastructure in Canada tends to be more expensive for a variety of reasons. So we selected this number of 3.6 here. We had other parameters being used for the simulation, and as Joanne mentioned, we had the relatively bad size to be notified that one parameter was wrong, which had a direct impact on our results. We were made aware of this only this morning, so we were able to update our results very quickly. But the results I'm going to present now haven't gone through a thorough review process due to need to update them very quickly. So we run a number of tests using a simulator, and the first test is we assume that the entire truck heavy flows from to Toronto and then the US border switch to eHighway, and we look at the payback periods of the infrastructure. So the simple payback period simply appears after which the savings totally pay back the infrastructure investment. So with the value for the avoided ton of CO2 ranging from $50 here to the maximum 170 from the federal policy, we see that the payback period for the entire corridor can go from approximately 10 to 20 years, which isn't bad for a large infrastructure. And relatively obviously, the payback period is significantly better on from Montreal to the US border, where the truck flows are significantly higher, and the payback is much longer for the most northwestern part of the highway, that from Quebec up north to less relevant for the technology. The second test that we ran was to try to simulate something more reasonable in terms of technology deployment. So let's assume that each highway segment will be electrified one after the other, starting with this one from Toronto to Prescott, that's close to Ottawa. Then the one to the US border, and then going up north to Montreal, and then Quebec City and Rivière-du-Loup. We also made assumptions on the adoption by the end industry, and we try to be realistic. So in the first years, we have just a few hundred heavy trucks that switch to the technology, corresponding to 0.4% of the current existing truck fleet. And then as the infrastructure is deployed, we assume that the adoption goes up and up, reaching in the end something like 30% of the heavy truck fleet from Ontario plus Quebec. And in this configuration, So we have an investment of 4.1 billion to build infrastructure and 1 billion for the trucks. This 1 billion is a comparison between the truck equipped with a pantograph and a small buffer battery to use the eHighway. So that's the actual investment for pantograph plus buffer battery as compared with a regular diesel powered truck. In terms of benefits, we have GHG emission reduction of 2.5 million tons of CO2 equivalent and savings on fuel of a bit more than 300 million. And we check what the economic internal rate of return of infrastructure is, so taking into account those investment costs and benefits. And we find that as long as the value of a ton of CO2 is above $85 per ton, the rate of return is positive. And it reaches 5%, their assumption of 170 ton of CO2. 5% is not extremely high, but again, for that kind of infrastructure is not totally unreasonable. The last test that we ran was to check how sensitive the results are to various parameters, because we are studying a technology that is not yet commercially deployed. So it was important for us to understand how uncertainty on some parameters impact the result. And what we find is that the cost per individual truck, the cost of electricity, and the operation and maintenance of the infrastructure do not have a major impact on the results. But what does have a major impact on the economic viability is obviously the cost of the infrastructure and also the rate of adoption of the technology. So in conclusion, one major uncertainty that we have right now is the adoption of the technology. Is the industry interested in switching to the eHighway? We see that there are many advantages in doing so, but will it be compatible with the trucking industry's own constraints and operational parameters? We also need to make sure that, yeah, indeed, it is relevant for the heavy truck industry. One thing that we have not included in the simulation is everything that relates to financing structure and financing cost. Who pays for the eHighway? What's the cost of financing? This, of course, has an important impact on the viability. Another parameter that's closely related is how are the benefits shared between the infrastructure provider and the trucking companies that will use it. So basically, a truck that uses the eHighway, how much will they have to pay for using it, and how will they contribute to the initial investment cost? This, of course, will have an impact on the adoption rate by the industry. There are many other feasibility considerations, for instance, clearance issues, issues related to the harsh Canadian winters that we have discussed a bit in our paper. And a last interesting thing is that the eHighway can be used in different configurations with different functionalities. What we have modeled here is for trucks to directly use electricity from the catenary on electricity as long as the overhead line, and then switch to an alternative energy source. But there are options, for instance, using the overhead line to recharge bigger batteries. So you need shorter stretch of overhead lines, which reduces the infrastructure cost, but you need higher investment per truck because each truck needs to be equipped with a bigger battery. That's something we've not looked at, but would definitely deserve.
Oh, seems that we have a technical problem, and we
just so you know, unfortunately, Clara lives in a rural area, so the connection is never very reliable.
So I think she's back online.
Yeah.
So So maybe providing high-speed internet will be higher on the list of the government than the eHighway, huh?
But the worst part is that it's right next to Ottawa. In Mashna, which is not far.
Yeah, too close to power to. Yeah. So Clara, you're back online.
Hey, sorry, I'm back.
Okay, you can. You have anything to add on your presentation, or we can start the question period right now?
That was the conclusion. So yeah, if there are any questions.
Yeah, so let's open the floor to questions.
Clara, this is Hassan from CPCS. You have mentioned to take into account the capex cost, but have you taken into account the operational and maintenance cost as well?
Yes, sure. It's included in the simulator. We assumed that the annual O&M would be 2% of the initial infrastructure. It's a very rough approximation, but it's hard to tell because the technology is still new.
Yes, normally for the high voltage transmission systems, electric transmission systems, I mean, the operation and maintenance cost is around 2 to 2.5%. So it's a valid assumption, I think so.
Thanks.
One question from the chat, Stephen, if you want to ask it directly, you can just open your mic.
Thanks. Yes, I'm just wondering about travel times being affected through this technological approach. For instance, like you know the apparatus comes loose from the electrical wire, and then needing to reattach it, there can be delays caused by that, as well as lane switching. I know freight are not always supposed to do that, but anybody driving on the highway sees it all the time, to them to be able to move a little bit faster, and reduction in lane switching, I presume, is going to lead to longer commuting times and so forth, and eating into cost.
Those are extremely good questions. Actually, a pantograph is a dynamic device, so can go up and down and connect and disconnect from the overhead line extremely quickly, and that's already what happens in light rail and train systems. So if the truck loses the connection for a short time, they have a buffer battery that covers that. And if they need to disconnect for a longer period of time, they also have a secondary engine, and connection disconnection is instantaneous. There is no lag time for that. And similarly, when they need to take over another truck, they can just disconnect from the overhead line and reconnect whenever they are in the lane. So actually, travel times are rather better with highway than, for instance, with 100% electric battery powered trucks, because you don't need to recharge your battery with the eHighway, so you save on the travel time.
Just a follow-up with that, like I'm from Toronto, and I've taken this streetcar a lot there, so I'm guessing the pantograph technology is a little bit different that's being envisioned here. There's definitely times where it disconnects and it takes them forever to put that thing back on. So I guess that we're working with something different.
Well, no, that's a good point. I have not experienced the light rail system in Toronto. I'm personally come from France, where we have a lot of electrified trains, and we do experience that kind of problem with the pantograph. So I'm quite confident that a properly designed pantograph for eHighway would not run into that too often. But more generally, there are pilots going on, and that kind of question can be answered with the results from the pilots that are not yet published, but we're expecting them, and we will analyze them whenever they're available.
Yeah, thank you. And I'm quite sure that the Toronto tramway doesn't have any internal storage capacity, so that's probably why it stops often. Any other question? We have a minute and a half still. Well, I would have one. What about the how would be the energy build, knowing that we would go from one province to another. So would that be two separate systems for the billing, or?
I mean, that's exactly a super interesting question that we have not considered in our simulation right now, because we were looking at the overall benefits for the society. Moving forward, if there's technology, who pays for what is clearly a key question. I'm not an expert in toll road systems, but I think that modern technology really allows monitoring extremely precisely where a truck is and when it is using electricity or not. So I imagine that it's relatively easy to know which electricity from which system a truck is using and to bill accordingly.
Yeah.
That's just to add, that's exactly right. I think it's going to be a question of putting something in the metering that will be part of the truck. And actually, I would encourage, there's Patrick Ackerman, who is the specialist or leading the Siemens eHighway program that is dealing with all of these issues in the European context. So if there are some more technical issues about at that level or the trucks, I invite you to write to him.
Right. Okay, well, thank you. That's the end of the 30-minute presentation. Thank you very much for that interesting presentation. Before I leave you, I would just like to, since there is no other presentation to be held, it's the last session. I would like to make just one. I cannot share my screen. Sorry. Why? Okay, there it is. So I would like to take those just a few minutes to make a bit of.
Louis, sorry, Louis, just so you know, Patrick Ackerman is on the following, and he just put a post in the chat, so people can go get more info.
Yeah. So the link is in the chat for that video on catenary system. Thank you for mentioning that. Yeah. So like I was saying before we leave, and since there is no presentation after this of today, so I have no other dates to announce, I would like to make just a bit of self-promotion from the Energy Modeling Initiative and let you know that we just released a new set of models called the Economic Impact of Electrification Initiative, or EI squared, to make it short. And those are models that will evaluate the economical impact, like its name says, of either building some new electricity production capacity or some energy services like thermal comfort that been modeling so far. And this is kind of I would say like a rehearsal or a proof of concept of what could be the energy modeling center that has been proposed in last year, in the first year of the Energy Modeling Initiative, where this is one great way, one way of showing that yes, we can add value at data gathering, processing, and formatting of data, but also making it more accessible and adding a bit of transparency. So with that being said, I will just say thank you all. Stay safe and see you soon. Thank you.